Good day, grade 12 family, and welcome to my YouTube channel. In this video, we'll be focusing on forces, but to be more specific, we'll be dealing with beams with the uniformly distributed load. So be prepared and take your pen and your notebook and be ready to study. Before we discuss the goals of this lesson, or rather the lesson objectives, let us quickly do a revision of what we already know, what we have learned in grade 11. We know that beams are used in anything. I mean, from our bridges, where they are used as a support system to support the bridge desk, to the roof structures, where they are actually being used to distribute weight to the walls. Now, what are these beams? We have learned from grade 11 and grade 10 that a beam is a horizontal structural element that carries a vertical load. Because beams they usually carry abnormal loads. It is for that reason that they are designed to support loads, or they must be designed in a way that they support a load. It is important, we know that, to know what a shear force and a bending moment that will be acting on a beam when designing a beam. It is very important to do what? To consider the shearing force and the bending moment that will act on that beam. So yeah, in this video we will be learning about beams with uniformly distributed loads. This lesson aims to ensure that after completing this lesson, every one of us is able to define what a uniformly distributed load is, to calculate the reactions and the bending moments, and also to draw the shear force and the bending moments diagrams. We have been focusing on beams with pinpoint loads, but the reality is that there are very few beams with only pinpoint loads. So that is why today we are discussing beams with what? With UDL, or the uniformly distributed load. Okay, let us discuss what is a UDL. A UDL is a load that is spread out over a certain distance. A UDL, it is indicated by a broken arrow and placed on top of a beam. They are replaced by an imaginary point load that is placed in the center of the UDL. This point is represented by dotted lines as shown in figure 1.2. Now, without any waste of time, let us take a look at the first example and solve it. Okay, example 1 says that a beam below is subjected to a 2-point load and 1 UDL, and it is supported by either end by RL and RR, as shown here on this problem. We have a beam which is a horizontal structural element that carries vertical loads. And then they saying that this beam, it is subjected to 2-point loads. It is subjected to 1 Newton point load and 3 Newton point load. With one UDL, and we said that we see an UDL by a broken arrow that is placed on top of a beam. So here it's our UDL. So this question says that we should calculate the magnitude of RL and RR. From grade 11, we learned the law of moments that states that a simple lever capable of turning about a given point or a fulcrum is loaded in such a manner as to keep it in equilibrium. And therefore, the sum of clockwise moments taken about a fulcrum will equal the sum of all the anti-clockwise moments. So even with this problem, we are going to acquire or we are going to use that knowledge. So they say that we must calculate an RL. But before doing anything, you cannot calculate anything or any beam with a UDL before actually converting the UDL into a point load. Always before you calculate a beam with an UDL, convert a UDL into a point load, or into an imaginary point load. You do this by multiplying the force per the force of the load per meter, which is 3 Newton meter. You multiply it by the length of the beam at which the force is acting into. So the length here it's 2. So it's 2 meter. So here we'll have a point load of 6 Newton meters. Moving on. Okay, so now we can calculate our RL and our RR. So we know, we have learned that from grade 11 that when you calculate, or when you want to find the the magnitude of RL, you need to use this formula that say for RL you need to take moments about RR. Take moments about RR. Once you have done that, you can now say that sum of upwards point loads as equals to sum of downwards point loads, in a sense that RL multiplied by total length of this beam, which is 8 meters. This is equals to this must be equal to, remember that we are taking moments about RR, so it's going to be the point load 3 Newton multiplied by a distance from RR, which is from RR to a 3 Newton point load, which is 2 meter, plus, remember now we have a 6 Newton that is represented by, we have an imaginary okay, let's write it here, a 6 Newton meter point load. We have it right here, and then remember that this will share this distance equally, so we will have 1 meter this side and also 1 meter that side. So we are coming here. Remember that we are moving from a point load to a point load. So we are coming to this imaginary point load on acting on a UDL, which is a 6 Newton meter. Sorry about that. We say that 6 Newton meter multiply by the distance from, sorry about that, as I was explaining that because we are taking moments about RR, so we are coming here to this imaginary point load to say that 6 Newton meter multiply by the distance from RR to this 6 Newton meter, which is 5 meters. 1 meter plus 2 meter plus 2 meter, it's 5 meters, plus 1 Newton pinpoint load multiplied by a distance from RR, which is 6 meter. So from here we know that we do maths to say that 3 Newton multiplied by 2 meter at 6 Newton meter plus 30 Newton meter. Oh, sorry, here it's my mistake. We have 6 Newton meter because we're going to apply the square root, and then the square root, they are going to cancel the meter squared, and then we'll be left with 6 Newton. So yeah, my bad, sorry about that. Plus 6 Newton meter plus 6 Newton meter. So because we know that we want RL, we are going to divide by 8 on both sides. So therefore RL 6 Newton meter plus 30 Newton meter plus 6 Newton meter divided by 8 meter is equals to our RL will be 5,25 newtons. For our RR, because the question said that we should calculate the magnitude of RL and RR. For our RR, we are going to say that RR take moments about RL. And then sum of upwards point loads must be equal to sum of a downward point load, in a sense that RR multiplied by total distance of a beam is equals to, now we are taking moments about RL. When you're taking moments about RL, we are going to say that 1 multiplied by the distance from RL, which is 2 meters, 1 Newton. Don't forget to write your SI units, plus we are on this point now, the imaginary point, which is 6 Newton, 6 Newton load point multiplied by this total length from RL, which is 3 meters. Going to plus that by 3 Newton point load, that will be multiplied by total distance of 6 meters from the RL. This here, it's 2 Newton meter plus 18 Newton meter plus 18 Newton meter, which will be divided by 8 meters because we want RR. Therefore, RR is equals to 4,75 newtons. We now have the value of RR and RL. Now let us prove that this statement here is correct. The sum of our upward forces, meaning RR plus RL, must be equal to sum of downwards forces. 5,25 plus 4,75, it's 10, and this over here also 6 plus 1 plus 3 is also 10. So therefore this beam, it is in equilibrium. So we can now move on and calculate the bending moment at A, B, and C as instructed by the question. So this is our question 1.2. We are calculating bending moment at A, B, and C. Now with bending moment, we know that what we are actually doing here, we are subtracting anti-clockwise or the downwards moment from the clockwise, which is the, we can take them as the upward point loads. So an easy way to do this, we learned that trick in grade 11. Sorry about that. It's where you will have to take a sheet of paper or a piece of paper and place it at a point which you want to calculate. And our question here says that we should calculate bending moment at A, B, and C. So at this instant, we were told to calculate the bending moment at A, so we placed our paper at A, And then the rule also say after you have placed a paper where at a point which you want to calculate, move from left to right, meaning from here we are going to move to the right. So yeah, when calculating the bending moment at A is equals to, remember that we said we are subtracting the downward point load from the upwards moment. So we do that in a sense that we're going to say that our RL, because this is in equilibrium, which is RL is equals to 5,25, R is equals to 4,75 Newton. Our 5,25 Newton multiplied by the distance to the paper, to where the paper is sitting, which is 2 meters, minus, because we are doing what? We are subtracting a downwards moment from the upward moment, minus, because the paper is sitting at 1 and there's no distance there, so we are going to say minus 1 Newton multiplied by 0, and anything multiplied by 0, we know that it is 0. So therefore bending moment at A will be equal to 10,5 Newton meter. Remember that the rule stated that we should now go from left to right. So moving from a point load to a point load. So moving to an imaginary point load there. An imaginary point load. Let us make it like this so that it is big enough. An imaginary point load acting in the middle. We will now have bending moment at B is equals to our 5,25 Newton multiplied by the total distance to the paper, which is 3. Remember, 3 meter. Remember that an UDL, it is placed in the middle and it is shared evenly. So the distance here was 2, it is now 1 and 1, they have shared, minus this point here, which is 1 multiplied by the total distance to the point. Okay, sorry about that. We always have to place.
Sure.
We always have to put a paper where a point is acting. So the mistake that we did with beam bending moment at B, it's that we have placed it and the imaginary point, and the force is actually acting here. So it will be our 5,25 Newton multiplied by 4, not 3. 4. and then this 1 Newton point load will be multiplied by 2 to a point where a distance where a point is actually acting, and then minus 6 Newton multiplied by this point here multiplied by 1 meter. Moving on, we know that this multiplied by 4, it's actually 21 Newton meter, and 1 Newton multiplied by 2, it's 2 Newton meter minus 6 Newton meter. This leaves us with a total of 13 Newton meter for bending moment at B. For bending moment at C, I hope that you're still learning. If you think that I'm moving too fast, you're more than free to pause the video and take your time as you are learning. Now, with bending moment at C, we will have to move the paper to this point. Now that we have moved the paper to point C, we can see that now our RL, our 5.25 Newton will be multiplied by total distance to the paper, which is 6 meter, minus, because we are subtracting downward moments from the upward moments, minus the 1 Newton point load, which will be multiplied by 4, and then minus 6 imaginary point load, the 6 Newton, which will be multiplied by a total distance of 3 meter, and then minus, because 3 Newton is acting on a point on C, there's no distance, so it's 3 Newton multiplied by 0. And this here we will have 31.5 Newton meter minus 4 Newton meter minus 18 Newton meter minus nothing, and this gives us a total of 9.5 Newton. And yes, that is that. We have answered the question. We have answered the question. We have calculated the bending moment acting on A, B, and C, and also we have calculated the reactions. Now we are coming to the last question of the example, where they say that with these findings over here, we should find the shear force. We should draw the shear force and the bending moment diagram. Now from grade 10 or from grade 11, we know that the first step we do here is that we project these lines all the way down. we do this. Now the second step here is to leave an enough space and then draw your reference point and label it at the upper plus and lower as minus. So that will be our reference point where our shear force will start. And then we will be, because our numbers are not that big, we have 5 and 4, we have 1, 6, and this is now like this. This is now like this. Let's remember. That it is over here. It is now represented by a 6 Newton imaginary point. So now the next step that you need to do after you have projected the lines all the way down, you'll have to choose a suitable scale, and here we'll be working with scale 1 Newton is equals to 1 centimeter. Okay, so from there we're saying that from our starting point we have an upwards force, or rather a reaction that goes, or rather a point of load that goes up with how many newtons? With 5. Our RL is equals to 5,25 newtons, and our RR is equals to 4,75 Newton. So we are saying that this force from here, it goes up with a force of 5,25. So 5,25, it's supposed to be somewhere here. You draw a line from your reference to your 5.25, and then they said that this force, it went to your right with a distance of 2 meters. With a distance of 2 meters. And then it experienced a UDL when it got between 1 Newton meter and 3 Newton meter. So a UDL in a shear force diagram, it is represented with a sloping line, with a line that slopes. So from here we are going that we are told that this force goes downwards by 1 meter. So remember that our scale says 1 Newton is equals to 1 centimeter. So we come here from this 1 centimeter, we measure 6 to this point. We measure 6. So 6 is somewhere here. Remember, an UDL is represented by a sloping line. Then from here, from the UDL, it goes inside with a distance of 2 meters. Always make sure that the spaces in your meters, they are always equal, please. That one you should always make sure of it. And then we are told that from here it goes down here with it goes down with 3 newtons. Oh, it's somewhere here. And then we are told also that it comes inside and then it will go back to 0. Remember that with shear force, we subtract what? We subtract we subtract also the what are they called? The point of loads. So it will be that for shear force at A, B and C. For shear force at A, we will have when we say that 5,25 minus 1, it will be 4,25 Newton. And then this 4,25 multiply by 6, it will give us a 1,75 Newton. And then from there we will have 1,75 Newton minus this 3 Newton going down is minus 4,75. So it goes back to 0 when it gets here, because negative 4,75 plus 4,75, it's 0. I'm hoping that you can see how we got to 0. Yeah, as I was saying that we'll start here at our point, which is 0. Our first value here is 10,5 Newton meter. And for here, let's use a scale of 1 Newton or is to 1 centimeter as well. 1 Newton meter is to 1 centimeter. So yeah, we'll say here, we'll come here and measure 10,5. 10,5, it's a lot. Okay, let's assume that 10,5, it's somewhere here. Let's assume that. And then come to this line where bending moment at B, they say that it's 13. Let's say that 13 is on top there. And then assume also that, okay, this is 10.5, meaning 9.5 must be somewhere. So with a bending moment, a UDL is replaced or it is represented here with a curve. It's represented with a curve, while inertial force, it is represented with a sloping line. So here we'll say that this from 0 goes to 10 there, and then with that curve, it's going to bending moment at B, then goes smoothly to C, and it goes back to 0. So yeah, our bending moment for this kind of problem will look like this. If there are any questions, don't be afraid to write them at the comment sections, and I will read them, and in our next meeting I will discuss first the questions. But that's all for me for today, and thank you.